Welcome. There's nothing you need to do right now but settle in, let your breathing slow and deepen, find a comfortable place where your body can rest. Tonight we're traveling together to the top of the world, to a place of ice and endless sky, where the ocean floats frozen beneath your feet and time itself bends in strange and beautiful ways. Just before we begin, I want to say thank you for tuning in to the Deep Sleep Discoveries channel. Please consider liking this video and leaving a comment below. It helps others find their way here too, one sleepy soul at a time. And now, let's begin our journey to the North Pole. The North Pole sits in the middle of the Arctic Ocean, floating on sea ice that drifts constantly, a wandering point that never stays quite still. There is no solid ground beneath this place, no bedrock or soil, only the deep ocean moving in slow currents far below the frozen surface. The ice you would stand on is itself a kind of raft, carried by winds and tides in patterns that trace circles across the top of the world. This is a place that exists and yet never quite remains in the same location, a moving target at the center of everything, the stillness at the heart of perpetual motion. The ice creaks and groans as it shifts, singing its quiet song to the stars above. There is no land beneath the North Pole, only ocean water approximately 13,980 feet deep at that exact point, a distance so profound that if you dropped a stone it would fall for nearly 3 miles before touching the seafloor. The water beneath the ice is dark and cold, holding secrets in its depths, layers of current and temperature stacked like pages in a book. This ocean remains liquid even in the coldest months, kept from freezing by the salt dissolved within it and the constant motion of its waters. The depth changes slightly as the ice drifts across underwater ridges and valleys, the floor of this ocean rising and falling in mountains no eye has ever seen directly. The ice at the North Pole is typically 6 to 10 feet thick, a frozen platform strong enough to hold the weight of a person, a camp, even aircraft that have landed there over the decades. This thickness varies with the seasons, growing in winter as the cold deepens and thinning in summer when the sun circles endlessly overhead. The ice is not smooth but textured, sculptured by wind and pressure into ridges and plains, a landscape of frozen waves. Beneath your feet, if you stood there, would be this layer of crystalline water, and beneath that the dark ocean, and beneath that miles of cold salt water descending into blackness. The ice breathes in its own way, expanding and contracting with temperature changes measured in fractions of degrees. The North Pole's position shifts approximately 40 feet per day due to drifting ice, which means the precise point where all longitude lines converge is constantly moving across the surface of the frozen ocean. If you planted a flag at the exact North Pole and returned the next day, you would find yourself 40 feet away from true north, carried along by the ice like a passenger on an incredibly slow train. This drift follows patterns influenced by winds, ocean currents, and the rotation of the Earth itself. Explorers who reach the pole often take photographs quickly, knowing that within minutes they will have drifted away from the mathematical center of the world. It is a destination that refuses to stay put, a goal that moves even as you stand upon it. The Arctic Ocean is the smallest and shallowest of Earth's 5 oceans, a body of water that feels almost intimate compared to the vast Pacific or Atlantic, yet it holds mysteries all its own. This ocean covers approximately 5.5 million square miles, most of it locked beneath ice for much of the year. Its average depth is only 3,900 feet, making it a shallow basin in oceanic terms, though still profound beyond human scale. The Arctic Ocean connects to other oceans through narrow straits and channels, exchanging water in currents that take decades to complete their circuits. It is an ocean that knows darkness half the year and light the other half, an ocean that lives beneath a ceiling of ice. The North Pole experiences 6 months of continuous daylight and 6 months of continuous darkness, a rhythm so different from the daily sunrise and sunset most of Earth knows. During summer, the sun circles the horizon day after day, never setting, casting long shadows that rotate slowly around you as if the world were a giant sundial. During winter, darkness settles in completely, broken only by starlight and the occasional shimmer of aurora overhead. This pattern emerges from the tilt of Earth's axis, the way our planet leans as it orbits the sun, bringing the poles alternately toward and away from our star. Life at the pole, if there were permanent life there, would follow seasons measured not in days, but in the slow turning of months. The geographic North Pole and magnetic North Pole are two different locations, separated by hundreds of miles, each serving different purposes in how we understand our planet's geometry. The geographic North Pole is the fixed mathematical point where Earth's axis of rotation meets the surface, the point around which everything spins. The magnetic North Pole is where Earth's magnetic field lines point straight down, pulled by the churning molten iron in the planet's core. A compass needle points toward magnetic north, not true north, which means navigators must account for this difference when plotting courses. These two norths drift relative to each other, the magnetic pole wandering while the geographic pole holds steady in its spinning. The magnetic North Pole moves about 34 miles per year due to Earth's molten core dynamics, the swirling currents of liquid iron thousands of miles beneath our feet. This movement has accelerated in recent decades, the magnetic pole racing across the Canadian Arctic towards Siberia faster than at any time in recorded history. The core's motion creates our magnetic field, that invisible shield protecting Earth from solar radiation, and this same motion causes the field's north point to wander. Scientists track this movement carefully because navigation systems, both ancient compasses and modern GPS, depend on knowing where magnetic north lies. The pole's path is unpredictable, following the hidden choreography of Earth's deep interior. Temperature at the North Pole averages -40 degrees Fahrenheit in winter and 32 degrees Fahrenheit in summer, a range that might seem extreme but is actually less severe than Antarctica's brutal cold. The ocean beneath the ice acts as a kind of heater, releasing stored warmth that keeps the air above from reaching the utterly frigid temperatures found at the South Pole. In summer, temperatures hover right around the freezing point of fresh water, warm enough that the ice surface develops puddles and pools. In winter, the cold deepens into a dry, crystalline chill that makes breath freeze instantly into tiny ice particles. These temperatures create an environment at the very edge of what permits liquid water to exist. Temperatures at the North Pole can plunge as low as -58 degrees Fahrenheit, though nearby Arctic stations have recorded below -90 degrees Fahrenheit, cold so extreme it feels almost abstract. At these temperatures, exposed skin freezes in minutes, and breath forms clouds of ice crystals that hang in the air like diamond dust. The metal of scientific instruments becomes brittle, and any moisture freezes instantly into patterns of frost. Yet even this cold is not the deepest Earth can offer. The South Pole experiences temperatures far more severe. The cold at the North Pole is tempered by the ocean's presence, that vast reservoir of water that cannot freeze completely due to its salt content and depth. Despite extreme cold, the North Pole is warmer than the South Pole due to ocean heat beneath the ice, a fundamental difference that shapes everything about these two opposite places. Antarctica is a continent, a landmass of rock and ice where temperatures can plummet to -130 degrees Fahrenheit. The North Pole floats on water that remains liquid beneath the ice, water that holds warmth the way a stone holds the sun's heat after sunset. This oceanic influence keeps North Pole temperatures relatively moderate, preventing the kind of absolute cold that grips the Antarctic interior. It is a warmth measured in comparison, still cold enough to kill, but not the coldest place on Earth. The Arctic ice cap has been shrinking by about 13% per decade since 1979, a change visible from space as satellites watch the white expanse diminish year after year. This retreat happens primarily in summer when ice melts back from its winter maximum, exposing more dark ocean water that absorbs sunlight instead of reflecting it. The trend appears in data gathered by satellites, submarines, research stations, a convergence of measurements all telling the same story. Scientists track this change carefully because the ice cap plays a crucial role in regulating Earth's temperature, acting as a massive mirror that sends solar energy back to space. Each decade's loss represents a shift in planetary systems that have remained stable for thousands of years. Multi-year ice that survives summers can still reach 10 to 12 feet thick, while first-year ice typically measures 3 to 6 feet, creating a textured landscape where different ages of ice mingle and stack upon each other. The thickest ice has survived multiple winters, building layer upon layer as snow falls and compresses, as seawater freezes beneath. This old ice becomes harder and less salty over time, the salt gradually migrating out through tiny channels and pores. First-year ice is younger, more fragile, more vulnerable to summer melting. The average thickness across the entire Arctic has declined significantly as more old ice melts away, replaced by younger, thinner ice that itself melts more easily the following summer. No time zones exist at the North Pole. All longitude lines converge there, making the concept of local time meaningless at this singular point. If you stood exactly at the pole and walked in any direction, you would be heading south, crossing time zones with every step. Research stations that operate near the pole typically adopt arbitrary time zones for convenience, often using the time zone of their home country regardless of solar position. The sun's movement provides no help in determining time here since it rises and sets only once per year. This temporal ambiguity adds to the pole's otherworldly nature, a place where human conventions about time and direction collapse into abstraction. Wind speeds at the North Pole average 10 to 15 miles per hour, much calmer than Antarctica, where hurricane-force winds scour the ice sheet relentlessly. The Arctic Ocean's relatively flat ice surface and the presence of water beneath create conditions where extreme winds are less common. When winds do pick up, they sculpt the ice into features called sastrugi, wind-carved ridges that look like frozen waves marching across the white expanse. These moderate winds are cold nonetheless, pulling heat from exposed surfaces with ruthless efficiency. The calm at the pole is relative, a gentleness measured against the violence possible in polar regions, where even a modest breeze carries teeth of cold that bite through any inadequate protection. The North Pole receives less precipitation than the Sahara Desert, only 4 to 6 inches annually, making this frozen world technically a polar desert, where water is abundant only in solid form. Snow falls in tiny amounts, adding slowly to the ice cap over months and years. The air at these temperatures is too cold to hold much moisture, so clouds are thin and infrequent. Snowfall is light and powdery. What appears to be a world of water is actually a place of profound dryness, where the atmosphere contains almost no vapor. The ice that defines the North Pole comes not from heavy snowfall, but from the freezing of the ocean's surface, a different process entirely than the snow accumulation that builds glaciers in other cold places. Snow at the North Pole is extremely dry and powdery due to extreme cold. Crystals so fine they squeak underfoot like styrofoam, so light they blow in the slightest breeze. This snow doesn't pack into snowballs or stick together the way warmer snow does. It remains granular and loose, a dust of ice that filters through your fingers. The crystals form in frigid air and fall slowly, growing into delicate structures that remain pristine until they land. This dry snow doesn't melt into your clothes but brushes off cleanly, and it reflects light with dazzling intensity. A million tiny mirrors scattering sunshine in all directions. Walking through it leaves footprints that look almost liquid, the snow flowing around your boots like a strange frozen fluid. The North Pole experiences polar stratospheric clouds that create rainbow-like nacreous displays, clouds so high and cold they exist at the very edge of space. These clouds form in the stratosphere, 15 to 25 miles above the surface, where temperatures drop below -108 degrees Fahrenheit. Ice crystals in these clouds diffract sunlight into iridescent colors, pinks, greens, blues, oranges, creating luminous veils across the sky. They appear most often during the twilight periods around polar sunrise and sunset, when the sun is below the horizon but its light still reaches these high-altitude clouds. Watching them is like seeing opals painted across the heavens, shifting and shimmering as the crystals tumble slowly in the thin air. Diamond dust, tiny ice crystals suspended in air, creates sparkling atmospheric effects that make the air itself seem to glitter in sunlight, as if you were breathing stars. These crystals form when water vapor freezes directly into ice without passing through a liquid stage, a process that happens in the clear, cold air above the pole. Walking through diamond dust is like moving through a cloud of microscopic gems, each crystal catching light and throwing it back in miniature flashes. The effect is especially pronounced when the sun hangs low on the horizon, backlighting the crystals so they glow against darker sky. It is one of the polar region's most magical phenomena, turning ordinary air into something luminous and strange. Temperature inversions are common, where air gets warmer as altitude increases, the opposite of the usual atmospheric pattern where higher elevations are colder. These inversions form when the ice surface radiates heat away into space, cooling the air directly above it while warmer air remains aloft like a lid over the cold. Sound travels strangely during inversions, carrying farther than usual, and optical effects can bend and distort distant objects into mirages. The inversion creates a stable atmospheric layer that traps pollution and fog near the surface, though at the North Pole there is little pollution to trap. This upside-down temperature structure is one more way the poles defy our expectations, creating an atmosphere that behaves differently than anywhere else on Earth. The Arctic experiences polar night, when the sun doesn't rise for months, darkness settling over the region like a season all its own, though not the absolute blackness you might imagine. During polar night at the North Pole itself, the sun remains below the horizon from late September through late March, 6 months when sunrise never comes. Yet this is not total darkness. The sky goes through shades of twilight, especially around what would be noon, when the sun approaches closest to the horizon without cresting it. Stars wheel overhead in their ancient patterns, and the moon traces its own path, sometimes providing enough light to read by when full. This darkness is profound but not complete, a dimness rather than blackness, a time when the world waits for light's return. During polar night, twilight can last for several hours despite no sunrise, the sky brightening and dimming in a slow rhythm as the sun approaches and recedes from the invisible horizon. This civil twilight creates enough light to see by, enough to distinguish shapes and navigate without artificial illumination. The twilight periods grow longer as the end of polar night approaches, dawn and dusk stretching toward each other until finally they meet and the sun returns. The quality of light during these hours is soft and diffuse, shadowless, coming equally from all directions as it scatters through the atmosphere. It is a liminal time, neither day nor night, a threshold state that can last for weeks near the polar sunrise and sunset. The sun at the North Pole rises once per year at the spring equinox and sets once per year at the fall equinox, a solar rhythm completely different from the daily cycles that govern most of Earth. The sunrise in March is gradual, the sun's edge appearing on the horizon and then disappearing again over several days as it spirals higher with each pass. Once fully risen, it circles the sky at a constant elevation that slowly increases until summer solstice, then decreases until it finally sinks below the horizon again in September. This long sunset reverses the sunrise process, the sun grazing the horizon multiple times before finally dropping below it for the winter. Each sunrise and sunset is not a moment, but a season, weeks when the sun plays at the edge of the world. At summer solstice, the sun circles the horizon at 23.5 degrees elevation, matching Earth's axial tilt, painting shadows in a complete circle around any vertical object over the course of 24 hours. The sun never climbs higher than this angle, never reaches overhead, but maintains this steady elevation as it makes its daily circuit. The light it casts is perpetually slanted, like permanent late afternoon, giving everything long shadows and warm tones despite the cold temperature. Standing at the North Pole on the summer solstice, you could watch your shadow point in every compass direction over the course of a day, a sundial measuring time in rotations rather than rising and setting. The sun becomes a patient timekeeper, marking hours by position rather than presence. Frost smoke, steam fog created when cold air meets warmer water, occurs at ice openings where the ocean is exposed, writhing columns of vapor that rise and dissipate like breath made visible. When a crack opens in the ice, exposing ocean water that is 30 degrees warmer than the air above, the temperature difference creates instant evaporation and condensation. The water vapor freezes into ice crystals almost immediately, creating a fog that looks like smoke billowing from the ocean's surface. This frost smoke can be dense enough to obscure visibility completely, and it carries the salty smell of open ocean into the cold air. These fog banks mark the locations of leads and polynyas, the breathing holes in the ice cap where ocean and atmosphere meet directly. Sea ice at the North Pole is constantly moving in a clockwise pattern called the Beaufort Gyre, a massive circular current that takes ice in a slow spiral across the Arctic Ocean. This gyre is driven by prevailing winds and ocean currents, a vast rotating system that can take several years to complete one circuit. Ice born on one side of the Arctic can drift across the pole and exit on the other side, traveling thousands of miles in its lifetime. The gyre is not uniform. It speeds up and slows down, expands and contracts with seasonal changes and climate variability. Understanding this motion is crucial for predicting where ice will be in future months and years, and for understanding how the Arctic system operates as a whole. Pressure ridges, walls of broken ice pushed upward, can reach 40 feet high, massive structures created when moving ice floes collide and crumple like slow-motion car crashes. These ridges form lines across the ice cap, barriers that explorers must navigate around or laboriously cross. Below the water's surface, pressure ridges extend downward even farther, keels of ice hanging into the ocean 4 or 5 times deeper than the visible ridge is tall. The formation of a pressure ridge is violent in geological terms, though it happens slowly enough that a person could walk away from the moving ice, the grinding and cracking audible from miles away. These ridges are some of the Arctic's most dramatic features, testament to the immense forces at work in the slowly moving ice. Leads, cracks in ice exposing open water, appear and disappear constantly. Dark lines cutting through the white landscape where tectonic forces pull the ice apart. These leads can open in hours, creating navigable channels through ice that was solid moments before, and they can close just as quickly. Ice floes grinding together and sealing the gap. Water in leads steams in cold air, creating frost smoke that marks their locations from miles away. For marine mammals like seals and whales, leads provide essential breathing holes and access to the surface. For human travelers, leads are obstacles that must be crossed on rubber boats or waited out until they freeze solid enough to traverse safely, the ice forming a thin skin overnight that may or may not bear weight. The Arctic Ocean contains approximately 1.4 million cubic miles of water, a volume almost impossible to visualize, roughly the same amount as all the Great Lakes multiplied by 200. This water is layered by temperature and salinity, stacked in sheets that mix slowly with each other. The ocean's volume is constant, but its surface expression changes dramatically, sometimes largely ice-covered, sometimes with vast areas of open water. All this water is connected to the other oceans, flowing in and out through narrow straits, exchanging heat and salt and nutrients in patterns that affect climate globally. It is a cold reservoir that stores and releases heat over years and decades, a thermal mass that moderates Arctic temperature swings and influences weather patterns thousands of miles away. Salinity of Arctic Ocean water is lower than other oceans due to freshwater input from rivers, with massive Siberian rivers pouring millions of gallons of river water into the Arctic basin every day. This freshwater floats on top of the denser saltwater, creating a stable layering that prevents mixing and keeps cold fresh water at the surface where it freezes more easily. The reduced salinity affects everything from ice formation to the organisms that live in these waters. River input varies seasonally, peaking in spring when snowmelt sends torrents northward, carrying nutrients and sediment that feed Arctic food webs. This freshwater influence makes the Arctic Ocean unique among Earth's oceans, a place where river and sea blur together in complex interactions. The ocean beneath the ice maintains a relatively constant temperature of 28 to 29 degrees Fahrenheit, cold enough to freeze fresh water but kept liquid by its salt content, stable year-round regardless of the air temperature far above. This water is at the freezing point for seawater. Any colder and it would begin forming ice crystals, so it exists in a delicate balance. The temperature stability comes from mixing, as currents stir the water column and prevent extreme cold from settling in layers. For organisms living in this water, the temperature is predictable, allowing adaptation to a narrow thermal range. This cold but stable environment supports life that would die in warmer waters, species tuned precisely to these conditions. Brine channels form within sea ice as salt is expelled during freezing, creating networks of tiny tubes where liquid saltwater remains trapped in the otherwise solid ice. When seawater freezes, freshwater molecules lock into ice crystals while salt is pushed out into these channels, which remain liquid because their increased salinity lowers their freezing point below the ice temperature. These channels are microscopic ecosystems where algae and bacteria thrive, finding shelter from the crushing cold outside. The channels branch and connect like veins through the ice, and their presence affects the ice's structural properties, making sea ice different from frozen freshwater in fundamental ways. As ice ages, these channels drain and the ice becomes fresher, harder, and clearer. Multi-year ice that survives multiple summers, is thicker and harder than first-year ice, dense enough to support aircraft and heavy equipment, bluish in color from compression and aging. This old ice has been through several cycles of melting and refreezing, each summer removing the freshest layer while the deeper ice remains. The result is ice that's almost as hard as rock, nearly salt-free, containing little air. Multi-year ice forms distinctive surface features, rounded hummocks and gentle ridges worn smooth by wind and sun. It represents ice that has successfully resisted melting, and each year it survives makes it more likely to survive future summers, though even ancient ice is vulnerable in a warming climate. Scientists can identify multi-year ice from space by its distinctive appearance and radar signature. Ice floes, large flat pieces of floating ice, can span several miles, vast platforms drifting slowly across the Arctic Ocean, temporary islands in a frozen sea. These floes are fragments of the ice cap, broken apart by leads and refrozen into discrete pieces that jostle against each other as winds and currents move them. Some floes are smooth and relatively flat, good platforms for research camps or landing strips. Others are jumbled and ridged, covered with pressure features and melt ponds. Standing on a large floe, you can feel almost like you're on solid ground until you remember that thousands of feet of cold ocean lie beneath your feet, that you're floating on what amounts to a raft of ice. The size distribution of floes affects how the ice cap behaves. Many small floes melt faster than fewer large ones. The Arctic Ocean stratifies into layers with different temperatures and salinities, stacked like a cocktail where denser liquids settle below lighter ones. At the surface is the relatively fresh, cold water from river input and ice melt. Below that is warmer, saltier water that originated in the Atlantic Ocean, entering the Arctic through deep channels. Deeper still is water from the Pacific, each layer maintaining its identity because they don't mix easily. This stratification is stable. It takes significant energy to overturn these layers, but it means warm water can be stored at depth, insulated from the surface by the cold, freshwater layer. If mixing increases, this warm water could rise and accelerate ice melting from below, a feedback loop scientists watch carefully. Polynyas, areas of open water surrounded by ice, serve as breathing holes for marine mammals, crucial oases in the frozen expanse where seals and whales can surface for air. These features form where upwelling brings warmer water to the surface, or where wind and currents prevent ice from forming, creating persistent open water areas even in winter. Some polynyas recur in the same locations year after year, like the Northwater polynya between Greenland and Canada, reliable enough that wildlife depends on them. The open water allows light to penetrate, supporting algae growth and attracting fish, making polynyas biodiversity hotspots in an otherwise uniform ice-covered environment. They are windows into the ocean, places where the barrier between water and air temporarily dissolves. Ice flowers, delicate frost crystals, bloom on newly formed sea ice surfaces, intricate structures that grow in hours when calm conditions and extreme cold coincide. These formations look like white roses made of ice, petals curling and overlapping, created by vapor that sublimates directly from the thin new ice and freezes into complex shapes. Ice flowers are fragile, destroyed by wind or temperature changes, lasting only until the next disturbance. They concentrate salt on their surfaces, making them many times saltier than the ice beneath. Scientists study ice flowers because they affect atmospheric chemistry, releasing bromine compounds that can destroy ozone, making these beautiful ephemeral structures important players in polar atmospheric processes. They are the ice's art, created and destroyed in the span of a single calm night. The albedo effect causes ice to reflect 80% of sunlight, keeping the region cold by bouncing solar energy back to space before it can warm anything. Fresh snow on ice reflects even more, sometimes 90%, making the Arctic ice cap one of Earth's brightest surfaces. This high reflectivity is crucial for maintaining polar cold. It's a feedback system where cold creates ice, which reflects light, which maintains cold. The ice acts like a planetary mirror, a climate regulator that helps keep the whole Earth's temperature balanced. Surface features affect albedo. Melt ponds are darker and absorb more light, as does dirty ice contaminated with dust or algae. Understanding albedo is key to predicting how fast ice will melt as climate changes. When ice melts, darker water absorbs 90% of sunlight, accelerating warming in what's called the ice albedo feedback loop, a self-reinforcing process where melting leads to more melting. Open ocean is nearly black compared to ice, transforming from reflective surface to absorptive one in a single season. The absorbed energy warms the water, which melts more ice from below and from the edges, expanding the dark area further. This feedback is why the Arctic is warming so much faster than other regions. Each bit of ice loss amplifies the warming, which causes more ice loss. It's a cascade that's difficult to stop once started, and it operates on seasonal and multi-year timescales, with each summer's melting affecting the next winter's recovery. Underwater ice formations called ice stalactites or brinicles grow downward like icicles, deadly structures that can kill bottom-dwelling organisms with their touch. These form when super cold, super salty brine excluded from forming ice sinks through the water column, its extreme salinity keeping it liquid despite sub-freezing temperature. As this brine descends, it freezes the water around it into a tube of ice that extends downward like a growing finger, sometimes reaching the ocean floor. If a brinicle touches sea stars or urchins, it can freeze them solid in minutes. These formations are rarely seen. They exist only in specific conditions of thin ice and calm water, but they're a reminder of how strange physics can become at these extreme temperatures, where water behaviors defy intuition. The aurora borealis appears frequently above the North Pole when solar particles interact with Earth's magnetic field, creating light shows that dance across the darkness of polar night. These auroras form when charged particles from the sun travel along magnetic field lines that funnel them toward the poles, where they collide with atmospheric gases and release energy as visible light. The displays can be subtle, a faint green glow on the horizon, or spectacular curtains of light that ripple and pulse across the entire sky. Standing beneath an aurora creates an almost supernatural feeling, watching light appear from nowhere, without source or shadow, purely atmospheric phenomenon made visible. The auroras follow the oval-shaped auroral zone that circles each magnetic pole, with the North Pole sometimes inside this zone, sometimes not. Aurora displays can extend 600 miles above Earth's surface, reaching into the thermosphere where the atmosphere becomes vanishingly thin, though the brightest displays occur between 60 and 200 miles up. The altitude affects the color. Different atmospheric gases dominate at different heights, and collision energy varies with altitude as well. The aurora's vertical extent is vast compared to other atmospheric phenomena. If you could see the aurora from the side, it would look like glowing curtains hanging from space, their tops far above where jets fly, their bottoms still well above the highest mountains. This high-altitude light show is visible across hundreds of miles of Earth's surface simultaneously, multiple observers seeing the same display from different angles, like watching a cosmic theater performance from various seats. Green auroras, the most common, occur when solar particles hit oxygen at 60 to 150 miles altitude. The collision exciting oxygen atoms into an unstable state that releases green light as they relax back to normal. This particular shade of green is distinctive, different from any other natural light source, a spectral emission line that appears nowhere else in daily experience. The green can be pale and diffuse or vivid and bright, sometimes forming defined arcs, sometimes swirling clouds that pulse and shift. Human eyes are particularly sensitive to this green wavelength, making these auroras especially visible even when relatively faint. When multiple factors align, strong solar activity, clear skies, dark night, the green aurora can be bright enough to read by, casting a strange ghostly illumination over the snow. Red auroras occur when particles hit oxygen above 150 miles, where the thinner atmosphere allows a different type of oxygen emission. one that produces deep red or scarlet light. These red auroras are less common and typically appear above green auroras, creating a two-tone display with green below and red above, though sometimes pure red auroras occur alone during particularly strong storms. The red is caused by the same element as the green, oxygen, but under different conditions of atmospheric density and collision energy. Red auroras can be subtle, barely visible to the eye but stunning in long exposure photographs. When very strong solar storms strike Earth, red auroras can be visible at much lower latitudes than usual, surprising observers who've never seen such displays before. Blue and purple auroras result from nitrogen interactions, this element producing a range of colors depending on whether it's molecular nitrogen or nitrogen atoms and how much energy the collision involves. Blue shows up most often at the lower edges of aurora displays, while purple can suffuse entire displays during intense storms. These colors are less common than green because nitrogen is less abundant than oxygen in the upper atmosphere, and the emissions are generally fainter. The blue has a distinct quality, almost electric, especially vivid against dark sky. Purple auroras can combine red from oxygen and blue from nitrogen, creating a blended hue that shifts as the display evolves. These multicolored displays are the most spectacular when all emission types occur simultaneously at different altitudes and intensities. Aurora curtains can stretch across thousands of miles of sky, vast sheets of light that appear to hang from the heavens, folded and pleated like fabric caught in a breeze. These curtains form along magnetic field lines, following the invisible geometry of Earth's magnetosphere. What looks like vertical fabric is actually aligned with the direction magnetic field lines dive into the atmosphere, particles following these lines like water down a drain. The curtains can be thin and delicate or broad and substantial. They can wave and ripple as the solar wind fluctuates, creating motion that seems almost alive. Multiple curtains can appear simultaneously at different distances, creating a sense of depth in the display, foreground and background sheets of light receding into the polar night. The aurora occasionally produces faint crackling sounds caused by electromagnetic discharge near the ground during strong displays, a phenomenon that puzzled scientists for decades since the aurora itself is too high up to produce audible sound. Recent research suggests these sounds originate much closer, perhaps only 60 to 200 feet above the ground, where temperature inversions trap electrical charges that discharge during intense geomagnetic activity. The sounds are described as crackles, pops, and rustles, typically heard only during the brightest displays and only in very quiet conditions where no other sounds mask them. These acoustic auroras are rare but real, adding another sensory dimension to the display, making what is usually a purely visual experience also audible, grounding the cosmic light show in something more immediately tangible. Solar storms can create aurora displays visible as far south as the Mediterranean, pushing the auroral oval dramatically equatorward when the sun unleashes particularly powerful bursts of particles toward Earth. Historical records describe red skies seen in Rome, in Greece, in Egypt during major geomagnetic storms, events that terrified observers who had never seen such phenomena. These extreme auroras indicate severe space weather that can also disrupt power grids, satellite communications, and navigation systems. The most famous was the Carrington event in 1859, when auroras were visible in tropical latitudes and telegraph systems sparked and failed. Such storms remind us that the aurora is not merely decorative but a visible symptom of powerful forces connecting Sun and Earth, normally confined to polar regions but capable of reaching anywhere during major events. The aurora follows Earth's magnetic field lines, creating oval shapes around poles rather than appearing exactly at the poles themselves, a ring of light that circles the magnetic pole at a distance determined by solar wind conditions. This auroral oval expands and contracts with geomagnetic activity. During quiet times, it shrinks toward the pole. During storms, it expands toward the equator. The North Pole can be inside the auroral oval, outside it, or right on the edge depending on conditions and the position of the magnetic pole, which is displaced from the geographic pole by hundreds of miles. Understanding this geometry helps predict where auroras will be visible, though the display's exact position shifts constantly with the fluctuating solar wind. The oval is a dynamic boundary, a glowing collar around the magnetic pole. Aurora activity follows an 11-year cycle matching the Sun's solar cycle, a rhythm of activity that peaks every 11 years when the Sun's magnetic field reverses and solar output reaches maximum. During solar maximum, sunspots are frequent, solar flares and coronal mass ejections launch more often, and auroras become more common and more intense. During solar minimum, the Sun quiets, auroras become less frequent and dimmer. This cycle has been tracked for centuries through sunspot observations, giving us a predictable pattern for aurora activity. We are currently in the rising phase of solar cycle 25, approaching maximum, meaning auroras should become increasingly spectacular over the next few years. The cycle reminds us that our star is not constant but variable, breathing in and out over years, its exhalations visible as dancing lights at Earth's poles. Robert Peary claimed to reach the North Pole first in 1909, though this remains disputed over a century later, questions lingering about his navigational methods and the speed of his final dash to the pole. Peary's claim was accepted for decades, made him famous, but modern analysis of his journals and photographs suggests he may have fallen short by 30 to 60 miles. The controversy centers on whether accurate position determination was possible with his equipment and whether his reported travel speeds were physically achievable. Regardless of whether he reached the exact pole, Peary's expedition was remarkable for its logistics and endurance, pushing into the Arctic when conditions were far harsher and support far less sophisticated than modern attempts. His disputed claim reminds us that exploration is as much about the stories we tell as the destinations we reach. Frederick Cook claimed to reach it in 1908, also disputed, his claim generally rejected by experts who found inconsistencies in his navigation records and photographs that seemed to show landscapes nowhere near the pole. Cook's claim preceded Peary's by a year, leading to a bitter public dispute between the two explorers, with Cook eventually being largely discredited. His story became a cautionary tale about the difficulty of verifying polar exploration before satellite navigation, when position depended on sextant sightings and dead reckoning methods with significant error margins in featureless terrain. The Cook-Peary controversy reveals how much early polar exploration relied on trust and reputation, verification being nearly impossible when returning with only journals and photographs from a landscape where every direction looks the same. The first verified surface conquest was by Ralph Plaisted's team in 1968 using snowmobiles, their position confirmed by aircraft flying overhead with navigation equipment sophisticated enough to determine their location definitively. Plaisted's expedition traded the romance of dogs and sledges for mechanical reliability, their snowmobiles consuming fuel but covering ground faster than traditional methods. The mechanical approach was controversial among purists, but it succeeded where others had fallen short. The verification came from US Air Force aircraft that could establish precise coordinates, finally removing the ambiguity that plagued earlier expeditions. Plaisted proved that reaching the pole was possible with modern equipment and navigation, opening the era of confirmed polar conquest. The first verified expedition on foot was led by Wally Herbert in 1969, traversing the Arctic Ocean from Alaska to Svalbard via the North Pole in a journey that lasted 16 months. Herbert's expedition was more than a dash to the pole. It was a comprehensive crossing of the Arctic Ocean with extensive scientific observations and navigation verified by sun sightings and aircraft overflights. Herbert lived on the ice through winter darkness, experiencing the full cycle of polar seasons while slowly working his way across the ocean. His expedition represented perhaps the last great journey of traditional polar exploration, combining old methods with new navigation technology. Herbert's achievement is sometimes overshadowed by the moon landing that same year, but it represented human endurance and skill in one of Earth's most demanding environments. The Soviet Union landed the first aircraft at the North Pole in 1948, a ski-equipped plane touching down on the ice to deliver supplies and personnel for scientific research. This aviation milestone opened the pole to regular visits, transforming it from an almost mythical destination to a place where scientists could establish camps and conduct sustained research. The aircraft approach bypassed months of surface travel, delivering people and equipment in hours instead of months. Soviet aviation in the Arctic was aggressive and ambitious, using military resources to establish presence and conduct research in regions they considered strategically important. The ability to land at the pole made it accessible in a new way, though landing on drifting ice remained dangerous, requiring careful reconnaissance to find ice thick and flat enough to support aircraft weight. The USS Nautilus became the first submarine to cross the North Pole underwater in 1958, passing beneath the ice cap in a feat that combined Cold War military strategy with genuine exploration. The submarine traveled completely submerged, using sonar and inertial navigation to find its way beneath ice that could extend 20 or 30 feet below the surface. Reaching the pole underwater was purely symbolic. The submarine detected no change in environment, but the accomplishment demonstrated capability and technological advancement. The Nautilus proved that submarines could operate beneath polar ice, opening possibilities for military transit and scientific research. The crew experienced the pole only as readings on instruments, a mathematical point passed in darkness and cold water, yet the achievement captured imagination worldwide. The USS Skate became the first submarine to surface at the North Pole in 1959, breaking through thin ice to establish that submarines could not only transit beneath the pole but also emerge there. Finding a thin spot suitable for surfacing required careful sonar work, searching for ice that was penetrable but solid enough to stand on once broken through. The Skate's crew held brief ceremonies on the ice, photographed the submarine in this unlikely location, then submerged again for the return journey. This capability had military implications. Submarines could hide beneath the ice and emerge anywhere, but it also enabled science, allowing research access to the central Arctic Ocean. The image of a submarine conning tower rising through Arctic ice became iconic of Cold War technological achievement. Russian nuclear icebreakers have been bringing tourists to the North Pole since 1991, massive ships that crush through multi-year ice to deliver paying passengers to the top of the world. These icebreakers are the only surface vessels capable of reliably reaching the pole during summer, their nuclear reactors providing unlimited power for weeks-long journeys. The ships are essentially floating towns, complete with dining halls, saunas, and lounges, making the journey comfortable if not entirely luxurious. Passengers can step onto the ice at the pole, a surreal experience made routine by the power of nuclear propulsion. The tourist expeditions transformed the North Pole from extreme destination to expensive but achievable goal, democratizing access while also raising questions about environmental impact and the commercialization of wilderness. The first hot air balloon to fly over the North Pole did so in 1996, drifting silently across the ice cap carried by winds while passengers looked down on the frozen ocean from a vantage point early explorers could only dream of. Ballooning over the pole combined adventure with gentleness, the balloon moving at wind speed, so passengers felt no breeze, hanging in quiet suspension while the ice passed below. The flight required careful planning, fuel for the burner, weather prediction, recovery arrangements, but offered a perspective unique from aircraft or surface travel. From the balloon's basket, the curvature of Earth becomes apparent, the ice cap spreading in all directions, the sense of being at the top of the world immediate and overwhelming. The balloon journey was slower and more contemplative than mechanized travel, closer in spirit to early exploration even while using modern technology. Birger Usland became the first person to reach the North Pole solo and unsupported in 1994, pulling his own supplies without resupply or assistance, walking alone across ice for almost 2 months. His journey represented the ultimate in self-reliance. No dogs, no companions, no supply drops, just one person and a sledge against the Arctic. Usland navigated leads alone, crossing them in his survival suit, swam through channels of open water that appeared suddenly, dealt with pressure ridges and mechanical failure without help. The psychological challenge matched the physical one. Weeks of isolation in a hostile environment where a serious injury would likely be fatal. His success proved that the pole was accessible to a skilled individual with modern equipment and sufficient determination, though replication remained beyond all but the most capable adventurers. In 2007, Russian submersibles planted a titanium flag on the seabed beneath the North Pole, 13,000 feet down in cold darkness where no light has ever reached naturally. The flag planting was symbolic, an assertion of Russian interest in Arctic territories, and sparked international controversy about territorial claims. The submersibles descended through cold water for hours, guided by sonar and navigation systems, searching for the ocean floor in absolute blackness. When they found it, they planted the flag in sediment that has been accumulating for millions of years, undisturbed until that moment. The flag remains there still, invisible, unseen, a human artifact in the deepest darkness of the Arctic Ocean, marker of national ambition in a place no nation can own. The North Pole Marathon has been held on the ice since 2002, an absurd and magnificent event where runners complete 26.2 miles on ice that shifts beneath their feet while they run. The course consists of loops around a small area near the pole, marked with flags, runners circling repeatedly in conditions that can reach -25 degrees. The ice is uneven. Runners navigate ridges and frost heaves, and altitude compounds difficulty since they're running at sea level in oxygen-depleted polar air. Finishing times are slow compared to temperate races, the cold, the terrain, the mental challenge all taking their toll, but completing a marathon at the North Pole is achievement regardless of time. The event transforms this hostile environment into arena for human endeavor, runners proving that play and competition can happen anywhere humans can reach. Drifting ice stations, research bases on floating ice, have studied the region since 1937, when Soviet scientists first established a camp on ice and allowed it to drift with currents while they conducted research. These stations consisted of tents and prefabricated buildings erected on stable ice floes, supplied by aircraft, occupied for months or years as they drifted slowly across the Arctic Ocean. Scientists at these stations conducted weather observations, oceanography, ice studies, experiencing conditions no land-based station could access. The stations eventually melted or broke up as ice deteriorated, requiring evacuation by aircraft or icebreaker. Dozens of such stations operated over decades, providing data about the Central Arctic that would have been impossible to gather any other way. Patient science conducted on a moving platform in one of Earth's most remote environments. Over 100 expeditions have attempted to reach the North Pole since 1900, some successful, some ending in rescue or retreat, a few in tragedy. The variety of attempts is remarkable. Skis, snowmobiles, dog sleds, parasails, even attempted bicycle journeys. Each expedition learned from predecessors, refining techniques and equipment, though the ice itself remained as unpredictable and dangerous as ever. Some expeditions made multiple attempts before succeeding, each failure teaching lessons that enabled eventual success. The cumulative knowledge from these expeditions transformed the North Pole from unknown to well-documented, though no amount of knowledge makes the journey easy. Each expedition writes itself into the story of human exploration, adding another chapter to our relationship with this extraordinary place. Modern GPS technology has made reaching the exact North Pole possible for the first time. Navigation satellites providing position accuracy within a few feet anywhere on Earth. Before GPS, determining exact position required sun sightings and complex calculations with significant error margins. Reaching the precise pole was mostly luck. Now travelers can watch GPS coordinates converge on 90 degrees north, can photograph themselves at the exact point where longitude lines meet. This precision removes some mystery, but enables science and verification that was previously impossible. GPS also makes polar travel safer. Rescue coordination becomes more reliable when distressed travelers can report exact positions. The technology democratized access to the pole while also making it somewhat less magical, trading uncertainty and mystery for precision and reliability. Polar bears occasionally reach the geographic North Pole itself. A mother and cubs were spotted at exactly 90 degrees north in 2006, proving these animals range farther from productive hunting grounds than previously believed. The sighting surprised scientists who assumed bears would stay near coastal ice where seals are abundant. The bears at the pole were likely traveling between hunting areas, crossing the Central Arctic Ocean in transit. Polar bears are capable long-distance travelers, swimming dozens of miles between ice floes, walking hundreds of miles in search of food. Their presence at the pole demonstrates the species' incredible adaptation and range, though it doesn't indicate the pole is good polar bear habitat. More likely, these bears were passing through on longer journeys to somewhere more hospitable. Arctic cod live in waters beneath the North Pole ice, small fish adapted to sub-freezing temperatures, able to survive by producing antifreeze proteins that prevent ice crystals from forming in their blood. These fish are key links in Arctic food webs, eating zooplankton and being eaten by seals, whales and seabirds. They live their entire lives in cold darkness beneath the ice, navigating by senses humans can barely understand, finding food in an environment that seems nearly lifeless. Arctic cod eggs float in the water column and juveniles hide in ice formations, using the ice itself as habitat and protection. The cod's ability to thrive in these conditions represents evolutionary success story, life persisting in conditions that would kill most other fish species almost instantly. Copepods, tiny crustaceans, thrive in Arctic waters and form the base of the food web. Countless billions of these creatures grazing on algae and being eaten by fish and other predators. These animals are each smaller than a grain of rice, yet collectively they form vast drifting clouds in the water column, visible on ships' sonar as layers of biological activity. Copepods are found throughout the world's oceans, but Arctic species have adapted to extreme cold, some entering dormancy during darkest winter months, others remaining active year-round. They convert microscopic algae into protein-rich packages that fuel everything above them in the food web. Without copepods, the Arctic ecosystem would collapse. They are the critical link between primary producers and larger animals, small creatures performing essential work in vast numbers. Algae grow on the underside of sea ice, creating an upside-down meadow invisible from above, a layer of photosynthetic life clinging to ice rather than rooted in soil. These algae use the dim light filtering through the ice, enough for photosynthesis even though it seems impossibly dark. The ice bottom is textured, offering surfaces for attachment, and brine channels provide nutrients. These algae bloom in spring when light returns, turning the ice's underside green-brown, creating grazing habitat for copepods and amphipods. The ice algae are uniquely adapted. They can photosynthesize at lower light levels than almost any other plant life, and they survive being scraped off and frozen repeatedly. This upside-down ecosystem is invisible unless you drill through the ice or use underwater cameras, a hidden world of life in an unexpected location. Jellyfish species, including lion's mane jellies, swim in Arctic waters, their translucent bodies drifting with currents, tentacles trailing for dozens of feet beneath their bells. These jellyfish are among the largest in the world, their bells reaching 6 feet across, their tentacles capable of delivering painful stings to anything that brushes them. They drift beneath the ice edge where water meets air, feeding on fish and smaller jellies, their simple bodies requiring little energy to maintain. The sight of a massive jellyfish drifting beneath Arctic ice is otherworldly. Their bodies glow in underwater lights, pulsing slowly, tentacles waving like translucent curtains. These ancient animals, largely unchanged for hundreds of millions of years, find the Arctic waters suitable habitat despite the extreme conditions. Ringed seals create breathing holes in ice and can be found near the North Pole, chewing at ice from below to maintain openings they can use through winter. These seals are relatively small, weighing perhaps 100 pounds, beautifully adapted to life in the ice with a distinctive ring pattern in their fur. They use their teeth and flippers to keep breathing holes open even as ice thickens, working from below to prevent freezing solid. Female ringed seals excavate dens in snowdrifts on the ice surface, hidden cavities where they give birth to pups and nurse them through their first weeks. These seals are primary prey for polar bears, though they're wary and quick to dive when threatened. Their breathing holes dot the ice across the Arctic, essential access points maintained by constant effort. Arctic terns migrate from Antarctica to the Arctic, experiencing 2 summers per year and seeing more daylight than any other animal on Earth. These small seabirds fly approximately 44,000 miles annually, pole to pole and back, following summer and avoiding winter in the ultimate seasonal migration. They feed on small fish and invertebrates, hovering over water and diving to catch prey. Arctic terns have been known to fly over the North Pole itself, making them among the few flying animals to visit this location. Their lightweight bodies and efficient flight allow this remarkable journey, though why they undertake such extreme migration remains somewhat mysterious. The energetic cost must be justified by the benefits of accessing 2 productive high-latitude summers each year, but the calculus is complex and not fully understood. Narwhals, whales with spiral tusks, inhabit waters south of the North Pole, though they rarely venture to the pole itself, preferring areas where cracks and leads provide access to air and where prey is more abundant. These medium-sized whales are instantly recognizable by the male's tusk, actually an overgrown tooth that spirals counterclockwise and can reach 10 feet long. The tusk's function has been debated, likely a sensory organ detecting water salinity and temperature, possibly used in social displays or feeding. Narwhals are deep divers, descending over 5,000 feet, hunting for halibut and cod on the ocean floor. They're highly adapted to ice-covered waters, able to navigate beneath solid ice and find small openings for breathing. Their calls, clicks, whistles, and trumpet sounds echo through the Arctic water, communication in a world where visibility is limited. Amphipods, small crustaceans, live in crevices within the ice itself, making homes in the frozen structure, grazing on algae growing on ice surfaces. These creatures are typically less than an inch long, with laterally compressed bodies that let them slip into narrow spaces. Some species are nearly transparent, others colored to match their ice background. Amphipods are remarkably cold tolerant, remaining active at temperatures that would immobilize most other animals. They form an important part of ice ecosystems, numerous enough to provide food for fish and other predators. Some amphipods are predatory themselves, hunting even smaller organisms in the ice matrix. Their existence within the ice demonstrates that this frozen world is not dead but inhabited, containing networks of life in what appears to be solid structure. Bearded seals can dive 1,000 feet below the ice to feed, descending into darkness to hunt fish and invertebrates on the ocean floor. These large seals are named for their prominent whiskers, stiff sensory hairs that help them locate prey on the dark seabed by touch. They're bottom feeders, using their whiskers to probe sediment for clams, crabs, and flatfish. Bearded seals are among the largest Arctic seals, males weighing 800 pounds, their size requiring substantial food intake. They prefer shallower waters than the deep central Arctic, but they range widely, sometimes appearing near the pole. Their elaborate underwater songs carry for miles, acoustic displays used in courtship, long trills and whistles that make the Arctic Ocean less silent than it appears. These seals are important to Arctic peoples who hunt them sustainably for food and materials. Microorganisms called psychrophiles thrive in sub-freezing temperatures, bacteria and archaea that have evolved to function where most life cannot. Their cellular machinery adapted to work in extreme cold. These organisms inhabit ice crystals, brine channels, and supercold water, growing slowly but steadily even at temperatures well below freezing. Psychrophiles produce antifreeze proteins, maintain flexible cell membranes that don't freeze solid, and use enzymes that remain functional in cold that would halt ordinary biochemistry. These microbes are found throughout the Arctic, in ice, water, and sediments, occupying niches where competition is minimal because few other organisms can survive. Their existence expands our understanding of life's boundaries, demonstrating that biology can adapt to nearly any condition where liquid water exists, no matter how cold or dark or inhospitable it might seem. Ice algae can photosynthesize using the dim light that penetrates sea ice, working with light levels that seem impossibly low, less than 1% of surface light intensity. These algae contain high concentrations of photosynthetic pigments, absorbing nearly every photon that reaches them, converting this meager energy into growth with remarkable efficiency. They bloom in spring when days lengthen, but ice is still thick, creating a pulse of productivity that kickstarts the entire food web. The algae are specially adapted to cold. Their photosynthetic machinery works at temperatures that would shut down temperate species. They're also flexible about light. If more light appears, they can use it. If light is scarce, they persist. This flexibility makes them successful colonizers of the ice bottom, an environment where light conditions are unpredictable and generally poor. Arctic sharks, including Greenland sharks, swim in deep waters beneath the pole, massive animals that live almost entirely unseen in cold darkness. Greenland sharks are among the largest shark species, reaching 20 feet long, weighing over 2,000 pounds, with lifespans that can exceed 400 years, making them the longest-lived vertebrates known. They swim slowly through cold water, feeding on fish, seals, and carrion that sinks from above. Their meat contains a toxin that makes it inedible unless specially prepared, an odd trait for a top predator. These sharks are nearly blind. many hosting parasites that attach to their eyes, yet they thrive in their dark, cold world. They represent Arctic megafauna we rarely consider, animals going about their long lives beneath the ice, unseen and almost unknown. Bearded seals and ringed seals are among the few mammals that venture into the extreme high latitudes near the pole, these seals being better adapted to the conditions than larger predators who require more food. These seals can create breathing holes almost anywhere there's ice, giving them access to regions where natural openings are scarce. Their relatively small size means they need less prey than larger animals, and their adaptations to cold allow them to function in water that would quickly kill unadapted mammals. Both species are important prey for polar bears and Arctic peoples, links in food webs that connect microscopic algae to human communities. Their presence near the pole represents life's ability to push into extreme environments, to find ways to thrive even where conditions seem prohibitive, where most other large mammals cannot or will not venture. Zooplankton migrations create a vertical daily rhythm in Arctic waters, these tiny animals rising toward the surface at night and descending to depths during day, a pattern called diel vertical migration that occurs even beneath continuous darkness or light. The migration is driven by predation pressure. Zooplankton rise to feed in surface waters when visual predators can't see them, then retreat to depths for safety. This behavior creates a biological pulse, biomass moving up and down through the water column daily, visible on ships' sonar as a deep scattering layer that rises and falls. Even under 24-hour darkness, the migration continues, suggesting biological clocks keep running independent of external light cues. This hidden movement represents enormous energy transfer through the ocean, millions of small creatures ascending and descending in synchronized patterns. Ice cores from near the North Pole contain air bubbles preserving ancient atmospheres, tiny packets of air trapped when snow compressed into ice thousands of years ago. Scientists drill these cores and extract the bubbles, analyzing them for carbon dioxide, methane, and other gases, reconstructing past climates from the atmospheric composition. The bubbles are like messages from the past, direct samples of air breathed by mammoths and early humans. Each layer in the core represents a year of snowfall, creating a striped record of accumulation and melting. The deepest parts of a core contain the oldest ice and oldest air, some bubbles holding atmosphere from over 100,000 years ago. This frozen archive is irreplaceable, offering windows into climates that existed before human civilization, helping us understand natural climate variability and human impacts. The Arctic Ocean acts as a heat reservoir affecting global climate patterns, storing summer warmth and releasing it through winter, moderating temperature swings that would be more extreme without this thermal mass. Ocean heat capacity is much higher than air's, so water can store enormous energy without large temperature changes. This stored heat affects atmospheric circulation, ocean currents, and ice formation patterns. When the Arctic Ocean has more open water, it stores more heat, which can delay fall freeze-up and affect winter weather patterns thousands of miles away. The ocean's role as heat reservoir means Arctic changes ripple outward, affecting weather and climate across the Northern Hemisphere. Understanding these connections is crucial for predicting how Arctic changes will affect global climate, effects that extend far beyond the polar region itself. Salinity measurements help scientists track ocean circulation patterns, the saltiness of water revealing where it came from and where it's going. Fresh water is lighter than salt water, so salinity differences create layers that drive circulation. By measuring salinity at different depths and locations, scientists can map currents and water mass movements, tracking how the Arctic Ocean exchanges water with the Atlantic and Pacific. Salinity also affects freezing point. Saltier water freezes at lower temperature, so salinity measurements help predict ice formation. Changes in salinity over time indicate shifts in precipitation, river input, and ice melting patterns, all components of climate change. These measurements seem simple, but they reveal complex ocean behaviors, circulation patterns that move heat, nutrients, and organisms across thousands of miles. Seismic studies reveal the ocean floor spreading at the Gackel Ridge beneath the Arctic, a mid-ocean ridge where tectonic plates are pulling apart and new ocean floor is forming. This ridge is one of Earth's slowest spreading ridges, separating at less than an inch per year, yet even this slow spreading creates earthquakes and volcanic activity. The Gakkel Ridge is extremely deep, much of it over 2 miles below the surface, making it difficult to study. Recent research found active volcanism along parts of the ridge, hydrothermal vents spewing mineral-rich water into the cold ocean, creating oases of unusual life. The ridge is splitting Eurasia from North America, a process happening so slowly it's imperceptible to human senses but fundamental to Earth's geological functioning. Studying this ridge helps us understand not just the Arctic but plate tectonics globally. Ice thickness measurements using submarines provide climate change data spanning decades. These vessels using upward-looking sonar to profile the ice they pass beneath. Submarines have crisscrossed the Arctic since the 1950s, creating a long-term data set of ice thickness measurements. Comparing modern measurements to historical data shows clear thinning. Ice that was 12 to 15 feet thick in the 60s is now 6 to 9 feet thick on average. Submarines can access areas year-round that surface ships cannot reach, providing data from deep winter when ice is thickest. Their measurements are precise. Sonar can detect thickness changes of inches, making them valuable tools for climate monitoring. Military vessels conducting other missions gather scientific data as a secondary benefit, an unusual collaboration between defense and research interests. The North Pole region releases methane from thawing underwater permafrost, frozen soil that formed on land during ice ages when sea level was lower and is now submerged and warming. As this permafrost thaws, it releases methane that has been frozen for thousands of years, methane that's a potent greenhouse gas. Scientists have observed methane bubbles rising from the seafloor in Arctic waters, sometimes in large enough quantities to create surface disturbances. This methane release is a climate feedback. Warming thaws permafrost, which releases methane, which increases warming, which thaws more permafrost. The magnitude of this feedback remains uncertain, but it's a concern because large additional methane release could accelerate climate change significantly. Monitoring these emissions helps scientists understand this feedback and predict future climate trajectories. Atmospheric research stations study how Arctic conditions affect global weather, measuring temperature, pressure, humidity, wind, and aerosols that influence climate beyond the polar region. The Arctic affects mid-latitude weather through phenomena like the polar vortex, a circulation pattern that can wander southward and bring extreme cold to lower latitudes. Research stations on ice and at coastal sites track these patterns, providing data for weather models that predict conditions weeks in advance. They also study Arctic haze, pollution transported from lower latitudes, and how aerosols affect cloud formation and precipitation. Understanding Arctic atmospheric processes is crucial because changes there affect everyone. Jet stream patterns, storm tracks, and temperature distributions all connect to Arctic conditions. The stations are often remote and difficult to maintain, but they provide irreplaceable data. Ocean acidification in Arctic waters occurs faster than in warmer seas, the cold water able to dissolve more carbon dioxide, which lowers pH and makes the ocean more acidic. This acidification threatens organisms that build shells from calcium carbonate. As pH drops, shell formation becomes more difficult, and existing shells can dissolve. Arctic organisms are adapted to cold but not to acidic conditions, so the change challenges them. Species like pteropods, small swimming snails, are especially vulnerable, and they're important food for fish and whales, so their decline could affect entire food webs. Arctic waters are naturally closer to saturation levels, where calcium carbonate becomes unstable, so they reach critical thresholds sooner than tropical or temperate oceans. Monitoring Arctic acidification provides early warning of changes that will eventually affect all oceans. Satellite measurements track ice extent with precision down to inches, space-based sensors observing the Arctic continuously from hundreds of miles up. These satellites use various technologies: passive microwave sensors that see through clouds, radar that detects ice surface characteristics, visible light cameras that capture detailed images. The data streams are continuous, creating daily maps of ice extent, concentration, age, and movement. Scientists combine measurements from multiple satellites to create comprehensive pictures of Arctic ice conditions. The satellite record now spans over 40 years, long enough to detect clear trends and natural variability. These measurements are objective and consistent, free from observer bias, making them ideal for tracking long-term changes. Satellites transform Arctic monitoring from difficult fieldwork to routine observation, though fieldwork remains essential for validating satellite measurements. The Arctic amplification effect causes the region to warm nearly 4 times faster than the global average, a phenomenon where polar regions experience amplified temperature changes compared to lower latitudes. This amplification has multiple causes. Loss of reflective ice exposes dark water that absorbs more heat. Atmospheric circulation changes transport more heat northward, and cloud feedbacks trap more warmth near the surface. The rapid warming is visible in temperature records, ice extent measurements, and ecosystem changes. Arctic amplification means that a global average temperature increase of 1 degree might correspond to 4 degrees in the Arctic, making the region a kind of planetary early warning system where climate changes appear first and most dramatically. Understanding why this amplification occurs helps us predict future changes and explains why the Arctic matters for global climate despite its small surface area. Indigenous peoples, including Inuit, have thrived in Arctic regions for over 4,000 years, developing cultures exquisitely adapted to life in the far north through accumulated knowledge and innovation. These peoples learned to hunt seals, whales, and caribou, to build shelters from snow and ice, to travel efficiently across frozen landscapes using dogs and sleds. Their traditional knowledge encompasses weather prediction, ice conditions, animal behavior, navigation without instruments, skills acquired over countless generations. Arctic peoples developed complex social systems, allowing them to survive in places where resources are scarce and conditions extreme. Their relationship with the environment is different from industrial cultures, based on intimate knowledge rather than technological control. These cultures persist today, adapting to modern circumstances while maintaining connections to traditional practices and values, proving that humans can live sustainably in the Arctic if they understand and respect its nature. The concept of Santa Claus living at the North Pole emerged in the 19th century as explorers pushed toward the poles, and the regions captured public imagination as remote, mysterious places perfect for locating magical figures. Earlier, Santa traditions placed him in Northern Europe or used no specific location, but American writers and illustrators gradually fixed his home at the North Pole, a place impossible to visit and therefore impossible to disprove. The North Pole worked symbolically. It's the top of the world, a place of extreme conditions requiring magic to inhabit, sufficiently remote that Santa could work without observation. This mythological association gave the North Pole cultural significance beyond its geographical reality, making it a place that means something to children worldwide, even though almost none will ever visit. The Santa connection shows how remote places become screens for imagination when their reality remains unknown. No permanent human settlements exist at the North Pole itself, the drifting ice making permanent habitation impossible, since any structure would drift away from the pole's position within days. Temporary camps have been established, research stations lasting weeks or months, but nothing permanent. The nearest permanent settlements are hundreds of miles away on coastlines and islands where land provides stable foundations. The North Pole remains one of the few places on Earth where humans cannot and do not live permanently, a wilderness of ice and water that refuses settlement. This uninhabitability preserves it as one of Earth's last truly wild places, unshaped by permanent human presence. The pole belongs to no one and everyone, accessible only temporarily, reverting to its natural state after visitors leave. Russian drifting stations have housed scientists for months at a time on the ice. These temporary bases erected on stable floes and supplied by aircraft until ice conditions forced evacuation. The longest operating station lasted over 9 years as its flow drifted completely across the Arctic Ocean. Scientists at these stations conducted weather observations, oceanography, ice studies, experiencing isolation and extreme conditions for their research. Life at a drifting station was challenging: constant cold, darkness in winter, perpetual light in summer, limited fresh food, and the knowledge that your base was slowly disintegrating beneath you. Despite hardships, these stations produced invaluable data about the central Arctic that couldn't be gathered any other way. The tradition continues with modern ice camps, though duration and frequency have changed. These stations represent scientific dedication, people willing to live on floating ice for months to advance human knowledge. The North Pole is considered international waters not owned by any nation, falling under maritime law governing the high seas. The Arctic Ocean is divided among surrounding nations: Canada, Russia, Denmark, Norway, and the United States, each controlling waters within their exclusive economic zones, but the Central Arctic, including the pole, remains international. This status means any nation's vessels can travel there, no permission required, though reaching the pole remains logistically challenging. The legal framework prevents any single nation from claiming exclusive rights, preserving the pole as common heritage. Disputes continue about underwater continental shelf extensions that might extend national claims toward the pole, but currently the pole itself belongs to no country. This international status is both practical, enforcing sovereignty over drifting ice would be impossible, and idealistic, the pole as shared space for all humanity. 5 countries, Russia, Canada, Denmark, Norway, and the United States, have Arctic territorial claims, their sovereignty extending into Arctic waters based on coastlines and continental shelves. These nations balance cooperation and competition, working together on environmental protection and scientific research, while disputing boundary lines and resource rights. Arctic Council brings these nations together with indigenous peoples' organizations to address shared concerns. Climate change makes Arctic waters more accessible, increasing economic interest in shipping routes and resource extraction, raising stakes for territorial disputes. The 5 nations conduct research to map underwater geology, supporting claims that continental shelves extend farther than initially thought. Despite disagreements, military conflict seems unlikely. The nations generally resolve disputes through negotiation and international law. The Arctic is emerging as a region of strategic importance where diplomacy and international cooperation will shape its future. The name Arctic comes from the Greek word Arctos, meaning bear, referring to the constellation Ursa Major, the Great Bear, visible in northern skies, the constellation pointing toward the North Star. Ancient Greeks used this constellation for navigation, its stars forming a pattern that remains visible year-round from northern latitudes. The region became Arctos because it lay beneath the Bear constellation under the Bear's watch. Antarctica, the opposite pole, takes its name as well. Ant-Arctos, opposite the Bear, though no corresponding southern constellation exists. This naming links the polar regions to ancient navigation and astronomy, celestial patterns guiding travelers before modern instruments. The bear reference is fitting too. Polar bears inhabit the Arctic, though they're named for the region rather than the region being named for them. Language carries history, and Arctic connects us to Greek sailors who looked up at stars and created frameworks for understanding their world. Early explorers believed in an ice-free open polar sea at the North Pole, theorizing that ice was merely coastal phenomenon and that the central Arctic held navigable open water. This theory was based on limited observations and hopeful speculation. Explorers who found open water leads assumed they were approaching ice-free regions. The theory persisted despite contradictory evidence, motivated partly by desires to find northern shipping routes to Asia. Multiple expeditions launched to find this mythical open sea, discovering instead that ice extends to the pole and beyond. The theory was finally abandoned in the late 19th century as more expeditions returned with consistent reports of ice-covered ocean. The open polar sea shows how exploration can be driven by misconceptions, how theories can persist without evidence when they align with economic or strategic interests. The Arctic defeated these theories with consistent ice, reality, overwhelming speculation. The North Pole serves as a reference point for all navigation systems, the fixed point from which we measure longitude and calculate bearings. Every navigation system, from magnetic compasses to GPS satellites, references the North Pole either directly or indirectly. The pole defines north on maps, the direction toward which compass needles point, or approximately point, given magnetic declination. Before modern navigation, determining latitude was relatively easy using sun altitude, but longitude required accurate timekeeping and complex calculation. The North Pole simplifies some of this. At the pole, longitude becomes meaningless since all lines converge there. Navigation satellites pass near the poles in their orbits, using the poles as geometric anchor points for their position calculations. The pole is reference and destination, the point that makes navigation possible yet is itself the place where navigation conventions break down. Every direction from the North Pole points south, making it Earth's ultimate compass point where conventional directions lose meaning and new ways of orienting become necessary. Standing at the pole, you cannot go north, east, or west, only south. This directional singularity is one of the pole's most disorienting aspects. Navigation at the pole requires different conventions. You might navigate by compass bearing relative to Greenwich Meridian or use GPS coordinates, but cardinal directions become abstractions. The pole is simultaneously the center of everything and nowhere special, a mathematical point with enormous symbolic weight but no particular physical distinction from the ice around it. This directional simplicity and complexity captures the pole's nature. It's the ultimate reference point that defies reference, the place where our mapping systems both begin and collapse, a location that's entirely ordinary and completely unique at the same time. We've traveled together to the top of the world, through ice and ocean and light and shadow, through the work of scientists and the journeys of explorers. Now it's time to rest. Let these facts drift in your mind like ice floes. Let your breathing slow and match the patient rhythms of the Arctic, where time moves differently and stillness is everywhere. There's nothing more you need to remember right now, nothing more you need to think about. Sleep well, knowing the North Pole will still be there tomorrow, spinning quietly, frozen and beautiful, a place you've visited in your mind. Good night.